Welcome back to Miss Eddie's Math Movies, where it's a cute to be a square. Today we're talking about section 1.2, which is conjectures and counterexamples. First, we're going to start with some important vocabulary. A conjecture is an unproven statement based on a pattern or observation. It's kind of like an educated guess, which you do a lot in science. The next is inductive reasoning. That's looking for patterns and making conjectures. So you're looking for a pattern and then taking an educated guess based on the pattern. You could compare this to deductive reasoning. So inductive versus deductive. This is using patterns, while this uses facts and properties. So that's the difference between inductive and deductive reasoning. And we use both in math class. Math is a lot about looking for patterns and making educated guesses, but we also spend time looking at facts and properties as well. A counterexample is an example that shows a conjecture is false. So we're going to show that our educated guess or someone else's educated guess is false. And we're going to practice that a lot. So let's dive right in and see what we come up with. Example 1, complete the conjecture. The sum of any two odd numbers is blank. All right, let's take this apart. Sum. Sum means the answer to an addition problem. So I'm going to put a plus sign there. Of two odd numbers. Okay, odd numbers are 3, 5, 7, 9. Okay. So we said the sum is the answer to an addition problem. We have to make sure we understand this conjecture before we finish it. The answer to an addition problem. And the odd numbers are 1, 3, 7, 9, 11, etc. So let's try out some examples to see what we get. All right, so we're going to add two odd numbers. So here's an example, 1 and 1. That's 2. That's odd and odd makes 2. Odd plus odd makes 6. Odd plus odd makes 10. Notice we have to do lots of examples to make sure we're really doing this right, to make a really good conjecture. Odd and odd again, another odd plus odd, and one more, 336. All right, so what do we notice? Every time we add two odd numbers, we get an even number. So to fill in this conjecture, to fill in this educated guess, because we use our inductive reasoning, right? Here's inductive reasoning right here. All of these, we looked at this pattern, and I'd say that the sum of any two odd numbers is even. We haven't proved it, but we're taking a pretty good educated guess at it. All right. Which of the following reasoning stages were used in example 1? Did we look for a pattern? Yes, we did. That's when we added all the odd numbers. Did we make a conjecture? Yes, we did. We said it was always even. But did we verify? We don't know for sure. We haven't tested all the odd numbers, so we can't have it completely verified. But we did do these two steps. Let's try another one. This one's a little bit trickier. All right, the sum of the first n odd positive integers is blank. Okay, we need to figure out what are they talking about here. We already know that sum means plus. Of the first n, right? N just stands for any number. Whatever number you tell me, maybe it's the first 2 odd positive integers or the first 7 odd positive integers. So let's talk. What are the odd positive integers? Well, integers is just like whole numbers, but positive or negative. But this tells us we just want positive, want them to be odd. So this is like what we just did. 1, 3, 5, 7, 9, etc. So when we add up the first 2 or the first 7 odd positive integers, what do we get? Okay, well let's check this out. Alright, we already talked about n. N refers to the number that how many do we want? So let's say we just want one odd positive integer. Well, here it is. We just want one of them. So the answer is 1, which is the same as 1 squared. Now you may be wondering, why are we doing this here? And you'll see, because that's going to show us the pattern. So what if n equals 2? So what if we want the first 2 odd positive integers? Well, that would be 1 and 3. So 1 plus 3 is 4. And 4 is the same as 2 squared. Okay, let's keep going. I don't know if we've noticed the pattern yet, but let's see what happens. What if we want 3 odd positive integers? So I want 1, 2, 3 odd positive integers. So 1 plus 3 plus 5 is 9, which is the same as 3 squared. Now maybe you're starting to see the pattern. 1 squared, 2 squared, 3 squared. Okay, so I'm going to guess that this answer is going to be 4 squared. Let's just check to make sure. We want 4 odd positive integers, so 1, 2, 3, 4. 1 plus 3 plus 5 plus 7. 1 plus 3 plus 5 plus 7 is 16. What do you know? It worked. I bet this one is going to be 25. 1 plus 3 plus 5 plus 7 is 16. 16 plus 9 is 25, which is the same as 5 squared. So if n equals 1, the answer is 1 squared. If n equals 2, the answer is 2 squared. N equals 3, 3 squared. So what if n is n? Then the sum would be n squared. So the sum of the first n, so any number we choose, the sum is going to be n squared if we're talking about odd positive integers. All right, so in the follow-up, we're going to check that theory. So if n equals 8, we think that the sum should be 8 squared, or 64. That's what our pattern told us. So let's see if that's really true. So the first odd positive integers, 1, 3, 5, 7, 9, 11, 13, 15. Now let's add all these up and see if we get 64. We know that 1 plus 3 plus 5 plus 7 plus 9 is 25. And check that in your calculator if you don't believe me. And 11 plus 13 plus 15 is 39. And 25 plus 39 is 64. Perfect. We made a conjecture that the answer was going to be 64, and we were correct. All right, I want you to try this now. And if you're up for a challenge, number 2 is a really good challenge. See if you can try that and get the correct answer. And we'll go over those in class. Finding a counterexample. All right, a counterexample, remember, is proving that a conjecture is false. So we have to show that this is false. So what I want you to write to the side, though, is really important. It's about finding a counterexample. So I want you to write, to find a counterexample, I must use the first statement, or the first part, use the first part, but prove the second wrong. And I'll show you exactly what that means, but this is really important to write down because we're going to use that a lot. So there's the conjecture. Here's the educated guess. The sum of two numbers is always greater than the larger of two numbers. Okay, so it's saying when we add two numbers, we always get a bigger number. That's what the conjecture is. Make sure we understand. When we add two numbers, we always get a larger number. All right, this is false, but we got to give an example why, right? That's what a counterexample is. So I must use the first part. So I have to use this. I have to sum two numbers. So I got to think of an example where I add two numbers, but not using the second part. So it says it's always greater. I have to show an example where it's not greater. So what about the numbers 0 and 3? If I add them together, is the answer bigger? Well, 0 plus 3 equals 3. Is 3 bigger than 0? Yes. But is 3 bigger than 3? No. So this is our counterexample. Notice I did the beginning part. I used the first part. I added two numbers. But then I proved this wrong. I showed it's not always greater. The sum is 3, which is not greater than 3. That means this conjecture is false. All right, last page. Ooh, use a different counterexample. All right, I want you to do this now. And we'll go over it in class. All right, here's our last example. Show the conjecture is false. Okay, so I have to use this beginning statement. That's what it means to find a counterexample. So all shapes with four sides of the same length are squares. So I have to find a shape with four sides the same length. I have to use this, but prove this part wrong. All right, so I need a shape with four sides the same length that's not a square. And here are some examples down here. This, look at all sides have the same length, but this is definitely not a square. So you can call this a diamond, or more formally, we call this a rhombus. So a rhombus is an example that proves this wrong. Because see, all these shapes have four sides the same length, but they are not squares. The conjecture is false. All right, I want you to try these now, and we will check them in class. This is M Cubed signing out.